Hello, welcome back. Let's continue our lecture. In this particular video, we're going to talk about Markov property and ethos process. So before we do that, let's take a closer look at the definition of financial products. In particular, when we talk about derivative product, what do we really mean? Well, as the name suggests, derivative product is really the price of this contract is dependent on the price of the underlying asset. For example, you have a stock option. The price of the stock option is derived or is dependent um, on the price of the underlying asset. However, you can actually expand this notion a little further. So you don't really have to have an underlying stock. You can be in general, it's the state of the world. So for example, if you have a weather derivative, you can actually say the price of the weather derivative depends on the temperature. So in that case, temperature is not really an asset, and the temperature is not a price of an asset, but then you do have a financial product, which is the weather derivatives, which is dependent on certain state of the world. So if the temperature is 27 degrees on that particular day, or the average of the month is a particular temperature, then you will have a particular price for that weather derivative. So in that case, instead of talking about derivative product, it's more in terms of contingent claim, contingent to a certain state of the world materialized. So that way of thinking will actually be helpful in the sense that you don't have to limit itself to just the price. So in certain situations, that notion will be more helpful. Now, the next concept we're going to talk about is called Markov property. So what exactly is that? Markov property basically means that for a particular stochastic process, that the variable, the state variable itself, depends. The change of the variable actually depends only on its current value. It does not depend on past value, meaning that it doesn't depend on the history. So if you have a Markov process, the future change or the future value does not depends on the past. So how did it get to right now is not important. What's important to the future value or the change of the current value is where it is right now, today. Whereas if you have a non-Markov process, then the change of the state variable or the future value of the state variable depends not only on its current value, but also on the history. By dependent on the history means that how you get to this point matters. So if you, let's say, have something depends on the stock price, then a Markov property will mean that, as long as the current stock price is so and so, you get this, your derivative will have this particular price. Whereas if the product has, there's a non-Markov property there, so we lose the Markov property, then the value of this asset not only depends on the current value of the stock, and also depends on how you get to this value. Is it, has it been going up to a particular boundary? If has went across a boundary, then the value may be different compared to a situation that in the history of this particular asset has never went across a particular boundary. So having a Markov property will greatly simplify our analysis. And so in our analysis here, we have a property for the underlying assets, where the underlying asset follow a stochastic process, which has this Markov property here. So let me give you an example why a simplified analysis. So you might have seen in other courses that you're using lattice method to price a derivative asset. So if you have the a Markov property, you'll end up with a recombining tree. So if it's up and down and up will get you to the same point. Whereas for if the underlying asset does not have the Markov property, i.e. is not a Markov process, the underlying process will form a tree like this, where a stock will go up and go down to a point where it's different from the stock is actually going down and going up. So whether whether the stock has gone up first, then go down, or has gone down later first and going up later matters. So they don't actually end up to the same point. If it gets to the same point, that means the information of whether it has gone up early first or it has gone down first doesn't matter. You will still end up to the same point. But if history matters, then you'll end up to different points. Now, having two different points means that you have a non-recombining tree, and your tree will have the node of the tree will increase exponentially. So here for a recombining tree, the first step 0, step 1 will have 2 nodes, and step 2 will have 3 nodes. So it increases linearly, 1, 2, 3, 4. But for a non-recombining tree is to the power n. So 1 will become 2 nodes, and they'll become 4. And then you have 1, 2, 3, 4, 5, 6, 7, 8. So it increases to the power n. And you will see that when you need to do numerical computation, it's after a very small number of steps, you will not have the amount of computational resources to handle this particular tree. So it becomes really, really complicated and almost impossible to calculate numerically. Now, but what enables us to have Markov property, right? So we can just assume that essentially it's from the economic theory, and in particular is from an economic theory that's called the weak form of market efficiency. So essentially that is saying that the current price contains all the information. So the future change of price of the financial asset depends only on its current price. Now, in the weak form of market efficiency, future change is irrelevant to the past history, but the future change is still relevant to the insider information. It can also have a strong form of market efficiency, which says that the future change of the price of the financial assets is independent on not just the current price, but anything current, like even you have insider information, it would really help. So for our purpose, the weak form of market efficiency is sufficient. Now, let's move on and talk about something called a Wiener process. A Wiener process is a stochastic process. It has a Markov property, and it forms the building block for something, more complicated. That by a process that we're gonna be utilized very often, called the Ito process. Now, a Wiener process, Z, is a stochastic process with the following two properties. Number one, the change of this state variable Z has a normal distribution, and the variance of that depends on the delta in order of delta t. The square root of delta t means that the standard deviation is in the order of square root of delta t. And a Wiener process, Z, follows a Markov process, which means the change on delta Z is only a function of time and a function of the current state variable Z, Zt, and does not depend on Zt minus 1, Zt minus 2, and so on. So it doesn't depend on this history. It only depends on the current state itself. This is where this blue text means, it's independent of any other Z, delta Z conditioned upon the realized value of Z. So the current realized value of Z is all you need to know to figure out what the distribution, in this case, of the future value. Now, Ito's process is built on top of Wiener process. So you see a delta Z here, and a Ito process is of the following form. So here, this is a discrete time form. So basically means a change of the state variable x has a component that is linearly with the change of the time, delta t. Now, this function itself, mu, can be a nonlinear function of x and t, but it's really mu times delta t. And also has a component here that is stochastic. So here it's deterministic. So because once we know the functional form mu here, a function of x and state variable x and time, if you know that this is deterministic function and then times delta t. But here is this function sigma here, which is also a function of the state variable x and t, but it's times the value of delta z, where delta z is actually a stochastic variable here, and it has a distribution. It has a normal distribution. And so then this times that will give a different variance for this stochastic process. Now, you can also obviously express them in a continuous form. So then you have a dx is equal to mu dt plus sigma times dz. Now, question will be which one is smoother? Is this the continuous process smoother than the discrete? By smooth, we mean doesn't have a whole lot of chunks. Like a smooth process has a finite length, where something smooth will have a longer length. So it wiggles a bit more, a lot more actually. So I'm actually, okay, let me see. I would actually ask that in class. I'm going to skip that, so we can talk about it in class. Which one is? The answer is the is that the discrete one is actually have a shorter path. So the continuous one is actually has more wiggle rooms. But the question is why? So I'm going to stop right here. And